Chapter 7, Electrical Devices, Troubleshooting, and Safety. Electrical Devices, Troubleshooting, and Safety. This chapter describes the process of locating the cause of malfunction electrical circuits associated with hydraulic control system information, includes testing devices, type of the ground points. Also addresses in the chapter safety measurement personnel should take when working on around electrical circuits. Hydraulic and electricals are often compared because of the systems of similarity. Hydraulic circuits require a power source, usually a pump, a load device, actuator, and conductor. Circuits differ mainly in the type of the device used to control to regulate hydraulic fluid. Type of the capacity actuator used to accomplish the work, which varies depending on the application. Electric circuit also requires power source, battery, generator, load device, light, bell, motor, proper connection, endorsement. Load device is also controlled, directs, and regulates the flow of electrical current. Hydraulic and electrical components are usually represented with diagrams of their own. Standardized simple electrical diagrams, often called schematics. Figure 7.172 page show the more common symbols. Hydraulic electrical similar circuits have many differences. For example, electric currents is invisible. Hydraulic fluid is not. Electric currents flow through solid wires. Hydraulic fluids flow through hollow lines. Figure 7.2 page 7.3 with the symbols show the electrical hydraulic components in Figure 7.3. Page 7.4 compares hydraulic circuit and electrical circuits. Troubleshooting electrical circuits. Electrical troubleshooting is process of locating the cause of malfunction electrical circuits. Following paragraphs contain some of the general troubleshooting information as well as specific type of determinative status of some electrical devices. Skills in troubleshooting electrical equipment circuits requires knowledge of electrical principles to understand how circuits and devices should function. Skill in reading and interpreting electrical schematic diagrams, product data, and so forth. Skill in operating, testing equipment, and interpreting test measurements. Ability to analyze programs in a logical manner. Following system steps to narrow down the problem in a small area of the equipment and such as most efficient with a trial and error method of troubleshooting. Alright, connectors connected, connectors not connected, battery, dry cell, DC power, AC power plug, fuse, lamps, single pole switch throw, single pole double throw switch, capacitor, resistor fixed, tapped resistor variable, or solenoid iron core, non-closed, non-open, relay contacts, non-open, non-closed, transformer, primary, secondary, cathode, anode, diode, ammeter, voltmeter, ohmmeter, earth ground, chassis ground, resistor restriction, generator power supply pump, ground, tank, capacitor, double spring loaded piston, switch, directional control valve, current flow, fluid flow, check valve, transformer, intensifier, comparison of electrical and hydraulic components. Alright, so you have your pressure tank, and then you have a pump and a power source motor, electrical, like relief, regular relief valve, and then restrictor relief into the vented tank. Whether they're the same pressure tank, I don't know. Pressure drop, restriction orifice, directional valve, load motor. Hydraulic circuit shows the voltage grounded from the power source to the generator to the motor. Another ground is to the regulation zero dynamic voltage drop, directional switch, load motor, and that's all grounded. Procedure detailed below can be very useful. Organizing problem-solving effort with the producing equipment downtime. Procedure for the following troubleshooting procedure consists of 5 steps that you should perform in order to represent the mobile, reliable method of learning and applying a logical approach. Problem solving that can apply with any equipment regardless of size. Step 1, identifying the system external identification, circuit the device non-functional correctly, identify the system, investigate the problem site with a sound, smell, touch. For example, the visible inspection of the equipment reveal the circuit component has overheated, change color of the indicator lamp which should not be on, is not. Peculiar odd may be lead to you discover metal insulation chatter noise with the indicated solenoid is about to fail. Moving controls, adjusting knobs may not change the problem or have no effect at all. the fact that the equipment is operating in its system. If someone else was operating the equipment when it failed, ask the person if he noticed anything unusual before it failed, finding noise, things that don't look quite right, improper operating sequence systems that can lead to the cause of the problem. If you cannot find an immediately identifiable system, try operating the equipment once you can determine to do so safely, what works and what does not work. Note anything that does not seem right, no matter how small. Take the time to conduct thorough investigation. Step 2, and analyze the system. In the system, identify the function where the systems indicate malfunction. Information obtained during the identification along the system and functional block diagrams. Knowledge of how the equipment is supposed to operate. Make logical technical deduction. For example, after careful examination, you find that a clamp of plastic injection molded machine will not pressurize further than analyzed without using test equipment arrows the problem to a clamp that is closed. Clamp pressurization pre-fit shift. Any of the other might contain the faulty circuit. Step 3, isolate the single faulty function. In this step, you will test the equipment and decide the faulty function actual causing malfunction. When making these tests following the guidelines, make only the tests that are safe to make. Make the tests least difficult to test. First, test those functions that eliminate one or more of the other possible faulty functions. For example, if you're taking an ohm-meter reading to determine the fault and you do not take the voltmeter reading as required, powers on the equipment, and you disassemble the half of the machine to reach it at the test point, perform a simpler test first. Test the midway point in the circuitry if possible. Good reading. Midway point eliminates preceding functions, indicate problems in remaining circuits. Faulty signal in the midway point means that the problem is in function and the process signal may be before the midway point. The injection molding example to test clamp pressurization circuit where the clamp fully closed single and input either eliminates function confirms the cause of the problem in the clamp. The not fully closed therefore cannot be pressurized. Continuing test input output spec functions until you identify and confirm the single faulty function. Step 4, isolate faulty circuit. In step, you can locate the single malfunction circuit with the functional group of the circuits. Use accumulated system test data to the closed single faulty circuit. Follow the guidelines from step 3, but apply them in the circuits related to the faulty function. Use schematic and block diagram to locate test points. The injection mold machine example assumes the clamp fully closed signal and does not present input. Clamp pressurization circuit test for the clamp's closed circuit used to identify the single faulty circuit of the first type may reveal that the output of the clamp's fully closed circuit is bad. A check of the input of the circuits may indicate that the input of the closed clamp limit switch is bad, but all the other good are good. You can now identify the problem as being associated with one of the relative few parts contained in a single circuit. Step 5, locate, verify the cause of the malfunction. Test you make with it identify the failing part of the faulty circuit. Test the circuit until you find the cause of the malfunction. Examine the test and fault and part of the verify it has caused the problem and produce the over-observed symptoms. And checking out the clamp's fully closed circuit, for example, to remove the suspected limited switch of the circuit, the test of the ohm meter to determine which switch contacts are closely correct. To complete the circuit, the contact for the ohm meter across the contacts for the switch, actuate the switch arm and several times to the checking of the meter reading. If the contact closed properly, the meter should read 0 ohms, but the arm is in the one position and the infinite with the arm is in the other position. If the meter point does not move, the switch arm actuated disassembled. Examine the switch. The last examination revealed the mechanical linkage connection switch arm contact is broken. Then you will find the cause of the malfunction. Final analysis shows that this cause explains the observed systems. However, the procedure is not complete until you have verified the findings. In this example, you would install a new limit switch in the circuit to operate the equipment to confirm that you have fixed the problem. Testing device following paragraphs outline some of the basic electrical tests you conduct with specific pieces of equipment that we'll discuss earlier. As part of the troubleshooting test, you should mechanically inspect these devices and spare parts are available to suitable good part of the suspected part. As a quick method of returning the equipment to operation to test the part and either repair it or discard it. Potentiometer, since the potentiometer is a variable resistant device, it should be disconnected and circuited to test with the ohm meter if suspected. If it is a suspect, only 2 of the 3 leads need to be disconnected for this test. Be very careful with adjusting the small potentiometers on the printed circuit board. They are quite fragile and can easily be broken if the rotary rotated beyond the end stop of the potentiometer as follows. Determine the existent resistance valve with a schematic diagram from the circuit. The value is also printed on the case of the device. Connect the ohm meter across the end of the potentiometer. Confirm that reading matches expected value. Remove the test lead with the once end of the move into the middle terminal. Rotate shaft, the term of the screw that varies the resistance of the device. The ohm meter reading shall indicate the 0 ohm on the one end of the shaft of the rotation. Fully expect the resistance value of the potentiometer on the other end. It should also show the smooth change if the resistance shaft is turned. Move the lead and still connected to the end of the terminal over the other end. Rotate shaft again, looking for the same smooth transition from 0 to maximum resistance. 2. Solenoid column coil. If the solenoid is thought to be faulty, remove it from the machine plug with the open port to the valve. If necessary, disassemble, examine the solenoid for signs of overheating and mechanical problems. Test the solenoid coil, attaching ammeter, set this to low resistant range. Check off the coil terminals. Coil is good, but the meter shall have the relatively low reading. A few thousand ohms or less zero reading, which indicate that the coil of the windings are shorted at each other, probably as a result of the melted insulation. Infinity reading an ammeter means that the coil is open and is defective. Relay. Test the suspected relay as follows. Actuate the relay armature manually. Remove the relay from the equipment. Examine the relay carefully with the sign of the mechanical problem. Check the relay coil, same way. Solenoid coil. If you don't find any mechanical problems, test the electrical contacts of the ammeter as you do with the switch contacts. Meter should read 0 when the contacts are closed, infinity when they are open. Test for the normally open and normally closed circuits. Transformer. When you determine a voltage reading system information, the transformer may cause the malfunction. Check the primary and secondary coil resistance for the ammeter. Disconnect one end of the primary winding, one end of the secondary winding for the rest of the circuit before testing, and the failure of the result of the opening winding of the ammeter will read infinity when connected across the defective winding. If the failure is caused by short turns with the winding, the problem is more difficult to diagnose because the ammeter will indicate the very low resistance. Since a winding consists of the length of the conductor wound into a coil, the resistant readings are normally quite low anyway. If you suspect short turns, you suspected primary and secondary operating voltage. Determine the appropriate turn ratio to divide the secondary voltage into the primary voltage to gear ratio. For example, 120 volts divided into 24 volts equals 5 to 1. Use this ratio to compare the measured primary resistance to measure the secondary resistance. Example, the primary resistance is 20 ohms, then the secondary resistance should be 4 ohms. Be assured that just 0 ohm could make the measurement. Hold the test to be insulated portion. You made it difficult to determine the reading of the cross since the measurement is close to the low end of the ohm scale. Compare the reading replacement transformer. If one is available to positively verify that the transformer is faulty, you may have to substitute a good transformer for a suspected one. Diode. You can simply resistance check with the ammeter to test the diode ability to pass current with the one direction only. Suspect the diode. Remove one end of the diode from the circuit connected with the positive ammeter. Leave the anode negative. Leave the anode ammeter is connected to the way with the diode is forward base of the measured reading. It should not be very low. So the ammeter for appropriate diode test range. Reverse the ammeter connection. The negative ammeter leads if attached to the anode. Positive lead. Test the cathode. The diode is reverse biased. The meter should have the higher resistance. Good diode should have a real low resistance forward base, high resistance reserve base. If the diode reads for the high resistance of the both direction, probably opening with the readings are low. In both direction, diode is short. The effective diode could be short in difference in the forward-back resistance. In this case, the ratio forward to the backward resistance and proper factor actual ratio depends on the type of the diode. As the rule of thumb, small single diode should have the ratio several hundred to 1. A power rectifier can operate the ratio as low as 10 to 1. In 7.3, the ground, every electrical circuit has the point of reference for the all circuit voltage compared with the reference point with the call of the ground. The circuit voltage are either positive or negative to the respective of the ground connection of the ground that are made with the save the reasons referred to the earth ground. When voltage measures are taken, a difference or potential between the point and circuit with the ground point is measured by a voltmeter. This type of the ground is referred to as chassis or common ground. An earth ground is naturally ground referred to the earth itself, since they represent with a point of 0 potential for the 0 volt short circuit device that connects the live voltage from the cause of a serious shock on anyone touching it. However, the frame is connected to the earth ground and is held with the safe potential for the 0 volts as either with itself will absorb the voltage. Today, a third-pronged ground power plugs connect most stationary equipment to the edge of the ground through the electrical wiring system. Some of the equipment is connected to the earth ground, but the conductor goes to the metal frame of the equipment. Two long copper rod has driven into the earth. Some of the appliances are often the ground connected to the conductor and the water pipe running into the ground. In any case, the frames of all the equipment conducted into the ground are at the same zero volt potential. This prevents shocks that might occur should the person touch two pieces of ungrounded equipment at the same time. Or your chassis and common ground. In some cases, electrical circuits have today, but not connected directly with the earth ground. However, the total require the point of reference for the common point with which elements each circuit are connected. For example, the portable battery-operated transistor radiator does not have the ground conductor connected into the earth. The strip of the conducting foil of the internal circuit board is used for the common point, but the automatic automobile motor battery is negative terminal is generally connected with the engine block or chassis frame by a heavy cable to the connecting point as well as the other point of the metal frame is considered to be the ground with electrical circuits on the vehicle, the rubber tie that insulates the vehicle with the earth ground. In these examples, the ground is simply a zero reference point at the electrical circuit referred to as the chassis ground. All voltage in the circuit are measured with respect to the common point. Alright, zero reference point. With a zero reference point, voltage cannot be expressed with a positive and negative A with the schematic diagram 7.4. Illustrate this point diagram. A show the voltmeter connected to two terminals, a 6-volt dry cell battery without a ground. In the circuit, the measured voltage 6 volt between the two terminals is neither positive nor voltage negative. Diagram B shows the negative battery terminal connected to the ground with the voltmeter measured for the difference potential between the positive of the terminal and. Alright, shows voltage reading without ground, positive terminal grounded, negative 6 volts, negative terminal grounded, positive 6 volts. Placement of ground provides both positive and negative voltage. The ground point, the measured voltage is 6 volts, but on a ground terminal, 6 volt with the most positive than ground. Zero reference point diagram shows the voltmeter segment of 6 volt positive terminal battery connected to 0 point on a ground battery. Now voltmeter. Reference point diagram B, 6 volt battery voltage between A and C is 12 volts. The ground placed between point A and B is in the two batteries. Now 6 volts is available between points A and 6. Held between points C and B, made modern electronic circuit that require both negative voltage for proper operation. This would be impossible with zero reference point in the circuit. D. Isolation between earth and chassis ground. Industrial equipment often requires earth and separate chassis ground for the proper operation. Earth ground represents the actual potential 0 volt. Chassis ground is usually a reference point with the same point below and above the earth ground. In this case, the earth ground and chassis ground are connected together at any point with equipment. However, during installation and repairs, chassis ground may inadvertently connect to the earth ground and check for the conditions of 1.5 dry D cell battery and holder. Connecting wire voltmeter and make sure equipment is off before making the test. In Figure 5.7.5 of the battery is insulated between the chassis ground with the earth ground voltmeter set with a measure 1.5 direct current connected across the battery. Connected against between the chassis and the earth ground, it would play for the short circuit with the cross of the battery. Voltmeter will indicate 0 volts. If this is the case, temporarily disconnect one end of the battery to keep the discharging while looking for the proper connecting between the grounds. When you find the connection, remove it. Reconnect with the battery of the meter. The voltmeter should read the battery potential 1.5 volt. Voltmeter reading is still 0 volts and proper connection still exists to the equipment. Repeat test of the voltmeter reading of the battery voltage. Remember to disconnect the battery after the testing, completing test. Safety. Effective safety measure of the blending of the common sense of the knowledge of the basic electrical hydraulic principles, how the system circuit operates, include the dangers associated with the operation. General safety information, safety practices are listed below. This is not inclusive. Not intended for the alter or replace currently established safety practices. Do not include these safety practices for hydraulic equipment. Information when working on electrical equipment. Consider the following information. Injuries associated with electrical work may include electrical shock, burns, puncture, laceration, abrasion, wounds. Current when flowing through the body can be fatal, as up to 1/10 of an amp. Produces perilous, extreme breathing difficulty. Average person, permanently physical damage. Death can result at 1/10 of an amp flowing through the heart. Amount of current received with electrical shock depends on the voltage applied with the resistant part of the body through the which current flows about 30 volts to produce 1/10 of an amp. So with extreme caution when working with circuits include the voltage higher than 30 volts. Most electrical shocks are unexpected. Everyone that is not particularly dangerous could result in the jerk hand with the heavier currents or hit some sharp objects. Always check the set the power is turned off the placing before your hand in the circuit. Practices when working electrical equipment. Consider the following safety. Never put both hands in the live circuit. Provides a path of the current flow through the heart. Keep one hand behind you in your pocket when taking measurements of within the meter. Never work on live circuits with wet. As the lower body resistance increases the chance of fatal shock. Never work alone. Electrical equipment. Shocks above 1/10 of an amp can paralyze your muscles and leave you unable to remove yourself from the source of the current flow. Always be sure someone else is around to help you in an emergency. Proper equipment and circuit test. Check for the correct junction settings and range switch. Proper insulation test probes and set forth. Remove all watches, springs, chains, any other metal jewelry that may come in contact with electrical potential. Get caught in moving mechanical parts. Do this before you work any electrical equipment, circuit, or battery. Have a good understanding about the circuit you are working on. Think about what you need to do before working on the circuit. Ask for your help if you don't know enough about the task you're to perform. And then Appendix A is the metric conversion charts, and we'll skip the appendixes.